This is a lecture 3E, which covers numerical surprises. Looking at this example, who played better? Cheryl had a higher shooting percentage both in the first half, 40% compared to 25%. See here. She did better. And in the second half, 75% is greater than 70%. Does this mean that Cheryl had the better shooting percentage for the overall total game? Let's take a look. The answer is no, but let's discuss why here. Based on the previous slide, we saw that Cheryl made 7 total baskets, 4 in the first half and 3 in the second half, out of 14 total shots. 10 in the first half, 4 in the second half. So she made 7 total out of 14 for a total game percentage of 50%. Candace, though, however, she had 8 total baskets that she made. She made 1 in the first and 7 in the second half, so that's a total of 8. And she also had 4 in the first half, 10 in the second half out of 14. And 8 out of 14 is actually better than 7 out of 14. She got 57.1%. So despite Cheryl having a better first percentage and a better second percentage, overall, she did not do better if you look at the game as a whole. This is one thing that can happen when we look at percents for just part of a game or part of a process versus looking at the whole process. So we do need to be very careful. Anytime you go and have a test done, so let's say you have a strep test or an influenza test, we have different outcomes that happen. A true positive means the result comes back positive and you are truly sick with that disease. A false positive means it comes back as, hey, yes, you have strep, but you actually don't. A true negative is when it comes back negative and say, no, you do not have this, and you don't. A false negative is when your test comes back negative, but you did still actually have it. And this happens in all sorts of tests because no test is 100% accurate. So here's an example of some positive and negative tests based on a tumor and whether it was cancerous or not. Remember that malignant means that those are your cancerous tumors. Your benign are your ones that are safe. They are fine. So in this table, we have the tumor was cancerous and it was tested positive 85 times. And it tested negative 15 times. So these ones down here are false negatives. They should have tested positive. And then over here, we also have false positives. So the tumor was benign. It was not cancerous. But out of these 10,000 people, 1,485 of them were told that it was actually cancerous. And then this one down here is true negative. So the test showed that the tumor was, in fact, negative. So the question then is asked, based on the numbers in this table, what is the percent of women with negative test results who actually do have cancer or who have a false negative? Well, so we want to look at all our negative tests here. So our total negative tests here are 8,430. And we want to know what percent of those are false negatives. So I'll see the work on the next slide. We knew that we had a total of 8,430 women with a negative test. And we also knew that 15 of those were false negatives. So to find the percent that were false negatives, we're going to take the number of women with that false negative out of the total number of women with negatives. This gives us the fraction 15 out of 8,430. Or the decimal 0.0018. And then if we times that by 100, that gives us 0.18% of women will get a false negative test if they tested negative. And if we think about this in terms of the 1,000 people, if we times that by 1,000, that would be just about 2 in 1,000. If we did this in our 10,000, we got our value of around 15. So needless to say, the chance that a woman with a negative mammogram actually has cancer is very small. So the likelihood of getting a false negative test with cancer is very small. Another way that we can look at these situations is with a tree diagram. So we're going to look at that for a polygraph situation. Suppose that 1,000 people are going to take a polygraph test and 10 of them are going to be set up to be lying. We also know the polygraph is 90% accurate. Well, how many of these applicants who were accused of lying were actually telling the truth? Well, if we have 1,000 applicants total and we know 10 of them lie, that leaves 990 that we know are going to be telling the truth. Now, we can go off of here and determine what percent or how many of each group are going to be true, positives, true, negatives, things like that. If the polygraph is 90% accurate, in the liars, it's going to catch 90% of them lying. So 90% of 10 is 9 liars, meaning that there's 1 liar over here that they're not going to catch. So this one's going to get away scot-free. They're going to say that this liar is telling the truth, and that's going to be a false positive. So this is a false positive. This one is correct. These are correct liars. And then we can do the same thing on the telling the truth side. If we have 990 that tell the truth, 90% of the test is going to show that these people are being truthful. So 90% of 990 is 891, are truthful. So these are our true positives. They're truly telling the truth. But the test is going to be wrong 10% of the time. And it's going to accuse some of these truth tellers to be liars. And that's going to happen 10% of the time. So 10% of the time, or 99 people, are going to be told that they are liars, false negative liars. And that's the answer we're looking for. How many of those who were accused of lying were actually telling the truth? Well, telling the truth, but accused of lying right here is 99 were falsely accused. Looking at another example here of high school drug testing. All athletes participating in a regional high school track and field championship must provide a urine sample for a drug test. Those who test positive for drugs are eliminated from the meet and suspended from competition for the following year. Studies show that at the laboratory selected, the drug tests are 95% accurate. Assume that 4% of the athletes actually use drugs. What fraction of the athletes who fail the test are falsely accused and therefore suspended without cause? I'm going to solve this 2 ways. The first way is we're just going to assume that there are 1,000 athletes total. Based on what we're told, 4% of those 1,000 or 40 athletes will actually be using drugs. And that means 960 athletes are not going to use the drugs. And we also know that the test is 95% accurate. So if that is true, 95% of the 40 athletes who use drugs, or 9.95 times 40, 38 athletes will test positive correctly. And the other 2 athletes who use drugs will test negative, giving us a false negative. Okay. Now, that's not part what we want, but this is just the first half of the solution. The next half is on the next slide. Now working with the 960 athletes who do not use drugs, we know that the test is going to be 95% accurate, saying that 95% of them are in fact negative. But 5% of them are going to test positive because the test is not fully accurate. So the number of athletes who are going to fail despite actually not using any drugs is 5% of the 960. So 0.05 times 960 is 48. So we've got 48 athletes who are going to test positive, but they are not actually positive. So now using what we got on the last slide, we had 38 positive drug users, and those were accurate. And we've got 48 positive drug users who were false positives. That is a total of 86 that are going to test positive out of the entire high school competition. Now, 48 of those 86 makes 56%. 56% are going to be testing positive when they do not, in fact, use them. So, despite having a 95% accuracy in this test, more than half of those that are suspended are actually innocent and should not have been suspended. Then on the next slide, we're going to talk about how we can view this in a tree diagram. So using a tree diagram, we can do the same process. We have all of our athletes up here, and they are broken into two groups. They either do not use drugs or they do use drugs. And then from each group, we know the test is either going to say correctly or incorrect. So of our users, we know the test is going to be correct 95% of the time. So these are positive for drugs, and they come back positive. That is a true statement. So how did I get this number down here? Well, I said 0.04 times 0.95, and I got this number here. So what this means is 3.8% of our athletes are correctly tested positive for drugs. Now, I can do the same thing over here. 0.04 times 0.05. 0.002 of our athletes are going to test negative despite actually being a drug user. So this is going to be a false negative. Now, on the non-drug user side, we've got 96% of our athletes. The test will be accurate 95% of the time. So 0.96 times 0.95 is going to give me this. The test will come back negative correctly for 91.2% of my athletes. But we have this group over here that are going to come back as positives when they shouldn't. So 0.96 times 0.05 gives me 0.048. And these are going to be my false positives. Now, the question asked, though, for all of the athletes that we look at, what fraction of the athletes who fail the test are falsely accused? So we want to see those that fail the test. Well, these fail the test. They are positive drug users, and they came back positive. These also failed the test. They are false positives. Okay? There was an accurate positive and a false positive. If you test positive for drugs, you failed the test. So we've got 0.038 over here and 0.048 over here, which if I add those together is 0.086. So out of the entire group of athletes, 8.6% test positive for drugs. Now, this is the false positives over here, and we want to know what percent that is. So 0.048 out of 0.086 times by 100 is going to give me 56% are false positives. And that is the exact same percent that we got on using the estimate of working with 1,000. So doesn't matter which one you prefer, they're both going to give us the same answer, and more than half of those that are testing positive are not true. Suppose the federal government spending for a popular education program was $100 million this year, and that Congress has proposed to increase this amount to $102 million for next year. Explain how this proposal can cause lobbyists who oppose the program to complain about the size of the increase, while lobbyists who support the program would complain that that is being cut. Assume that the consumer price index is expected to rise by 3%. As we know, in our government system here, we have taxes and things that happen all the time in our government that they're arguing back and forth. So these two graphs, one shows the rich pay more under tax cuts, and the other graph shows that high income householders actually receive the best benefit from these tax cuts. So they actually support opposing conclusions. So maybe if you have a second, you want to add a comment here to what you're seeing. But just goes to show that even if we think one thing is happening, we can have opposing conclusions for the same scenario. So back to our situation of what we could argue for both sides of this political spending as far as education goes. Well, we know that spending is rising. And if we're going from 1 million to 2 million, the opponents are going to just say, we're spending too much money. They're going to say, we're spending an extra 2 million. We don't want to spend it. Now, if we think about those that wanted this, they're going to complain about only increasing $2 million because our consumer price index rises by 3%. So if we have 1 million right now, that means we would need 103 million next year. So they're going to claim that this is not enough to be able to support what we're currently supporting based on the way inflation is occurring. So even though both will end up being unhappy about the situation, they're unhappy for different reasons. Let's look at an example for kidney stone treatment. The table below shows the results when two different techniques are used to treat large and small kidney stones. Each entry in the table gives the number of successful treatments and the total size of the treatment group. So in this table, we have two treatments, treatment 1 and 2, on both large and small kidney stones. First question says to verify that the table gives the following success rates expressed as percentages of each treatment in from above here. So all they're wanting us to do is make sure that is 81 divided by 87 times by 100 equal to 93%. And I will say, yes, it is. And then we can check the next one. 234 divided by 270 times 100, it will give you 87%. So I'm going to tell you that yes, it does work. You could verify these last two, but it is going to work. Question B. Which treatment has the higher success rate for small stones and for large stones? Well, if we look at just these two here, small stones do better with treatment 1. So small stones, treatment 1. And for large stones, if we look at large stones, the treatment 1 is also bigger. So they both do better under treatment 1. C. Now compute the success rate for both treatments when the cases of large and small stones are combined. So now we want to find the total for treatment 1. So I have to add 81 and 192. I get 273 out of a total of 87 plus 263 is 350. 273 out of 350. So treatment 1 gives me a 78% success rate. I'm going to do the same thing with treatment 2. So I'm going to combine all these together. 234 plus 55 is 289. Out of, if I take 270 plus 350, 270 plus 80 is 350. And then 289 out of 350, treatment 2's average overall is 83%. So which treatment actually has the higher overall success rate? And that is treatment 2. Treatment 2 overall did better, even though back here, so in B, when we looked at them individually, it looked like treatment 1 did better. But when you actually combine them together, treatment 2 was overall more successful. So that's why sometimes it seems surprising that even when you look at them by themselves, it's 1, but when you combine them together, it's 2. And then you can see how a researcher or someone could make you believe something by only looking at one of those 2 pieces. Suppose a test for a disease is 90% accurate for those who have the disease, true positive, and 90% accurate for those who do not have the disease, true negatives. Within a sample of 2,000 patients, the incidence rate of disease is the national average, which is 2%. Verify that the following entries in the table agree with that given information. So we want to verify that those with the disease is 2%. So with the disease, so disease here, we have a total of 40. 40 actually have the disease out of our total 2,000. 40 out of 2,000, times by 100 is going to give me 2%. Okay, next question says, of those with the disease, so again, we're working with this column here, they have to have the disease, what percent test positive? Well, we've got 40 with the disease and 36 of them tested positive. So 36 out of 40 times by 100 is 90%. Of those who test positive, what percent have the disease? So now we want to look different. Now we want to look at this row. Those who test positive, what percent have the disease? Well, 36 out of 232 have the disease, times by 100. And that's going to give me 15.5%. So clearly our test was not very good here with testing positive. We had a lot of them that tested positive when they were not actually sick. So explain why they're different. Well, we're working with different totals. First off, this B was working with those that had the disease. C is going to have a different result because we're working with those that tested positive. So we've got different values out of different totals. Last question. Of those who test positive, what percent do not have the disease? Well, test positive is this group here. Do not have the disease, that's 196 out of 232. Times it by 100. 84.5% did not actually have the disease. So this was not the best in when it tested positive here. We had a lot of false positives. All right, this is the end of section 3E. You have reached the end of what you need to watch for this week. So please go on and do your Pearson homework and your discussion board for this week. And I will see you next week for chapter 4.